This is a video walkthrough for practice 2a. In 1 and 2, we're given a relation between the variables x and y in the form of ordered pairs and asked to find its domain and range. So, in number 1, the domain is the set of all x values, which are the first numbers in each ordered pair. When we write the domain, we use the set notation, curly brackets, and then just write the numbers separated by comma that correspond to the x values. When we write the range, we choose the y values, which are the second numbers in each ordered pair, and that set contains the numbers 7, 8, and 9. Notice that there are only 3 numbers in that set because 8 is repeated and we don't list that one twice. Next, we're going to determine if this relation is or is not a function, and what we'll notice is that each domain value or each x value corresponds to only one y value. That is, when x is 1, y has to be 7. When x is 2, y has to be 8. When x is 3, y has to be 9. And when x is 4, y has to be 8. So this relation is a function since each x corresponds to only one y. In number 2, we can find the domain by listing the first values in each ordered pair, or the x values, and those x values are 0, 1, and 4. We can find the range by listing the y values, or the second number in each ordered pair. The range contains the numbers 2, 3, 4, and 5. Next, we'll determine if this relation is or is not a function, and to do so, let's consider each x value. Does x equals 4 correspond to only one y value? And the answer is yes. Does x equals 1 correspond to only one y value? And the answer is no. X equals 1 corresponds to both 4 and 2 as y values, so this relation is not a function. For number 3, the graph consists of a series of points that are not connected, so it is just a set of ordered pairs, much the same as the exercises above. When we find the when we find the domain, we're going to find the set of x values, which consist of the numbers -2, -1, 0, 1, 2, and 3. Remember to use the braces or curly brackets for that set. The set of all y values is the range, and that set begins with the smallest number, -3, followed by 0, followed by 2, followed by 3 is the largest y value. And this relation is a function because each x in the domain corresponds to only one y value. In number 4, we can write the ordered pairs and then find the set of all x values for the domain. From least to greatest, the set of all x values is -1, 0, 1, and 2. The set of all y values listed from least to greatest is -1, 0, 1, 2, 3, and 4. This relation is not a function because, for instance, the x value of 1 corresponds to more than one y value. X equals 1 corresponds to 0 and 4 as y values. For number 5, the domain now includes more than just a discrete set of numbers. Discrete means separate. So we're going to include all the values between x equals -4 and +2. So this will be given in the form of an inequality. The x values lie between -4 and +2 with the -4 included. remember that if the graph is connected, you're going to have to use an inequality to state your domain rather than just a set of discrete points. The range is the set of all y values. The smallest y value on the graph is 0, and the largest is 3. That's not exactly accurate. 0 is not included. 3 is included. Be sure that you are using the variable y when you're referring to the range. This graph is a function, and a really easy way to tell that is just to slide a vertical line along the graph of the function. Any vertical line that I draw only intersects the graph one point at a time. For number 6, our domain is the set of all y values, and our leftmost y value is -1. Our rightmost y value is +3. So we will state that x is between those two values, inclusive of both, and your inequalities need to point toward the smallest side, which is -1. For the y values, we need to start with the smallest of the y values, which is down here at the bottom of the graph. That is -3, and the highest y value is +3, and y is the variable between those, and the range is inclusive of both. This graph also passes the vertical line test. Any vertical line will only pass through one point at a time, so this relation is indeed a function. For number 7, the domain is the set of all x values. So our leftmost x value is -4, and because of the arrows on the end of the graph, there is no rightmost y value. So that means that our x values are always greater than or equal to -4. When we consider the range, we need to consider the smallest y value on the graph. At first, it might appear that that is the smallest or lowest point on the graph. However, the arrow indicates that the graph keeps going both right and down, and so there is no end to the lowest point on the graph. There is no highest point on the graph either, and so the range is all real numbers. All y values are included in this graph. However, when we pass a vertical line through this graph, you'll notice that it intersects twice, which makes this not a function. For number 8, our domain is the set of all x values. At first glance, that seems like the leftmost point, and that seems like the rightmost point. However, there is no end to the graph. The graph on both ends keeps going down and left, or right and up, and so the domain is all real numbers. Those points also seem like they would be the lowest and highest points on the graph, but again, the graph keeps going down and up, so the range is all real numbers. Let's pass a vertical line through this graph. Intersects once, intersects once, intersects once. It appears that a vertical line will never intersect more than once, so this graph this relation does represent a function. For number 9, our domain is the set of all x, and we do not have a leftmost point because of that arrow. The graph continues going left in that direction. However, the graph ends right here and then restarts on the right side and keeps going to the right. This is very much akin to a number line graph where there is no graph in the middle, so this indicates that we have a disjoint set for the domain, and that means that x is either less than or equal to -2, or x is greater than or equal to +2. For the range, we need to consider lowest and highest y values. That is the lowest point on the graph, and that occurs in two places. So the lowest value is -3, and the graph continues from there going upward without end, so that means that our y values will always be greater than or equal to -3. This relation is a function because any vertical line that passes through the function will pass through in one point only at a time. So this is a function, does pass the vertical line test. For number 10, our domain is indicated by the leftmost and rightmost values. The graph is connected in between, so the leftmost x is -1, the rightmost is 3, x is between those. Point the inequalities toward the smaller end, and then include or equal to's to show that those two x values are included in the graph. When we consider the y's, we'll look at the lowest and highest points on the graph, and every y value in between is included, so the lowest y value is -4, the highest y value is 0, y is in the middle. Point those inequalities toward the lower end, or the smallest end. This relation does not pass the vertical line test. If I pass a vertical line through the relation's graph, you'll notice that we intersect two points at a time, so there are two y's associated with one particular x, and so that means that this relation is not a function. All right, in number 11, we're asked to think about how the vertical line test is performed and then explain why it can be used to determine if the graph of a relation is a function. It would be good to refer to what we just did above and look at that vertical line. It's intersecting 2 points at once. And so for x equals 2, you can say that there are 2 y values for that particular x value, and therefore the graph is not a function. So when the vertical line test is performed, a vertical line intersects the graph in one point if there is only one y value for that x value. It will intersect in more than one point if there is, or there are, more than one y value for that x value. All right, in number 12 through 14, we have a relation between x and y. We're going to find the domain. Given the domain, we're going to find its range. And the hint is we're going to make a table of values and use each x to find the y. So for this particular relation, when x is -2, then y is -3 times -2, or 6, plus 1, which is 7. When x is -1, y is -3 times -1, which is 3, plus 1, which is 4. When x is 0, -3 times 0 is 0, plus 1 is 1. When x is 1, -3 times 1 is -3, plus 1 is -2. And when x is when x is +2, -3 times 2 is -6, plus 1 is -5. So our range is -5, -2, 1, 4, and 7, the set that includes those. For number 13, we can create a table of values again. And if the y value is equal to the x value squared, then -2 squared is 4, -1 squared is 1, 0 squared is 0, 1 squared is 1, 2 squared is 4. And so our range consists of 3 values only, 0, 1, and 4. For number 14, we can create a table of values. Our domain values are 0, 1, 4, and 9. And if x is equal to 0, then y squared equals 0, and y has to be 0. If x is 1, y squared is 1, but x can be positive or negative 1. Or rather, y can be positive or negative 1, because positive or negative 1 squared both give us 1. If x is 4, then y squared is 4, and y can be either positive or negative 2. And if x is 9, then y squared is 9, and y can be either positive or negative 3. That means that the range consists of the following values: -3, -2, -1, 0, 1, and 2, and 3. So we have several range values there. And in particular, you'll notice that this relation right here is not a function because there are more than one y value for each x value. In number 15 through 17, an equation describes a relationship between x and y. We're to determine if the relation is a function, and the hint is we're going to make a table of values like we did in the exercises above. So, for instance, in number 15, if x is -2, y is -1/2. If x is -1, y is -1. If x is 0, y is undefined, because 1 divided by 0 is undefined. If x is 1, y is 1. If x is 2, y is 1/2. It doesn't seem that we ever get more than one y value for each x value, so I'm going to declare that this is a function. For number 16, let's say that x is -2. If x is -2, we have to think -2 is equal to the absolute value of y. Is there any number whose absolute value is equal to -2? There is no y value to go with that one. And so now let's replace x with another value, -1. And again, there is no y value to go with that one. What if we replace x with 0? Then the y value has to be 0. The absolute value of 0 is 0. If we replace the x value with the number 1, then y can either be positive or -1. If we replace the x value with 2, then y can either be positive or -2. So I think what we found out here is that this is not a function because there are more than one y value associated with certain x values. Now let's consider y equals the absolute value of x. When x is -2, then y is equal to the absolute value of -2, which is 2. When x is -1, y is 1. When x is 0, y is 0. When x is 1, y is 1. When x is 2, y is 2. Each x corresponds to only one y, so this one is a function. For numbers 18 through 26, we're going to find each function value for the functions named at the right. Be careful that you are using the correct name for each function. F of 0, we're going to use the function f of x. So f of 0 is equal to 2 times 0 plus 1. Just replace the x value with 0, and that will give us 0 plus 1. That means that f of 0 equals 1. G of 3, we'll be working with the function g. So g of x is equal to 2x squared minus 4 times x. So g of 3 is 2 times 3 squared minus 4 times 3. We need to do our exponents first, then multiplication. And so g of 3 is equal to 6. Next, we're going to work with function h. And function h is h of x equals the square root of x plus 7. So h of 2 is equal to the square root of 2 plus 7, which is the square root of 9, which is equal to 3. For number 21, we're working with the function p. P of x is equal to x minus 1 divided by x plus 4. So p of 5 is 5 minus 1 divided by 5 plus 4. So p of 5 is 4/9. For number 22, we're working with the function f. And the function f of x is equal to 2 times x plus 1. F of negative 5 is 2 times negative 5 plus 1, which is negative 10 plus 1. So f of negative 5 is equal to negative 9. For number 23, we're working with the function g. G of x is 2x squared minus 4x, so g of negative 3 is 2 times negative 3 squared minus 4 times negative 3. We need to take care of our exponent first, and then our multiplications. That will give us 18 plus 12 is equal to 30. For number 24, we're working with the function h. H of x is equal to the square root of x plus 7. So h of negative 3 is the square root of negative 3 plus 7. We need to perform the operations inside the grouping first. Negative 3 plus 7 is 4. And so h of negative 3 is the square root of negative 4, or square root of 4, which is 2. For number 25, we're working with the function p. And the function p of x is equal to x minus 1 over x plus 4. So p of 1 is 1 minus 1 over 1 plus 4. And that will be 0 divided by 5. And 0 divided by 5 is 0. Make sure to simplify that fraction. In number 26, p of negative 4 is equal to negative 4 minus 1 divided by negative 4 plus 4, which gives us negative 5 divided by 0. And division by 0 is undefined, so p of negative 4 is undefined. Now, for each of the following functions, we're going to do something a little bit more involved. You'll notice that number 27 says f of 5 minus g of 1. All we need to do here simply is find f of 5, find g of 1, and then subtract them. So if you want to do part of the work in your head, f of 5 is 2 times 5 minus 3, which is 7. G of 1 is 1 squared minus 3 times 1, which will give us 1 minus 3, which is negative 2. 7 minus negative 2 is 9. For number 28, we're going to follow a similar pattern. We're going to find each one of those function values first, and when we find f of 4, we're going to eventually multiply it by 2. So f of 4 is 2 times 4 minus 3. That's 8 minus 3 is 5. Now g of 4 is 4 squared minus 3 times 4. That will be 16 minus 12 is 4. So now I just need to perform the rest of the operations. 10 plus 12 is equal to 22. For number 29, we're finding f of 3c plus 7. So that means that we're going to replace x with 3c plus 7. So f of 3c plus 7 is 2 times 3c plus 7 minus 3. Let's simplify that. That will be 6c plus 14 minus 3. So f of 3c plus 7 is equal to 6c plus 11. For number 30, we're working with the function g of x. G of x is equal to x squared minus 3x, so g of c minus 4 is equal to c minus 4 squared minus 3 times c minus 4. C minus 4 squared is c minus 4 times c minus 4. And now let's go ahead and do our multiplications. C minus 4 times c minus 4 is c squared minus 4c plus 16 minus 3c, now distributing the multiplication, plus 12. Be careful when distributing a negative. Now let's combine our like terms, so g of c minus 4 is equal to c squared, and now we have 3c terms. Minus 4, that's minus 8, minus 3 is minus 11c, and then plus 16 plus 12 is plus 28. For numbers 31 through 36, we're referring to the graph of y equals f of x. F of 4 is asking us to replace x with 4, and when we find what goes on the opposite side of the equal sign, we will be finding the y value. So when x is equal to 4, the y value is negative 2. Now, let's find in 32 f of negative 2. This time the x value is negative 2. When x is negative 2, the y value is negative 1. Now let's work with number 33. We're finding f of negative 4. So now the x value is negative 4. And what you'll notice over here on the graph is there's no point where x is negative 4. So that will be undefined. It hasn't been defined by the graph. Lastly, f of 3, when x is 3, the y value is negative 3. For 35, we're finding the values of x for which f of x is equal to 2. So the 2 represents the y value, and we are trying to find x. When f of x, or the y value, is 2, there is only one point on the graph that corresponds to that, and that would be x is equal to 1. When we're asked in number 36 to find the values of x for which f of x is equal to 0, when f of x, or y, is equal to 0, we'll notice there are 1, 2, 3 points where the graph intersects that horizontal line, and so those are at x equals negative 3, 0, and 2. Now in 37 through 42, we are referring to the graph of g of x, and we're finding g of negative 4. That means we're replacing x with negative 4. When we go to x equal negative 4, we find the y value is equal to 1. When x is negative 3, we find that the y value is 2. When x is 0, we find that the y value is 1. And when x is 5, which is way over here, we'll notice that there is no y value on the graph, so that would be undefined. For 41, for what values of x is g of x equal to 3? Here we are finding the x value given the y value. So the easiest way to do this is to draw a horizontal line where the y value is equal to 3. That line represents all points where the y value is equal to 3. There are 2 points on the graph that intersect, and so those intersect at x equals -2 and also +2. Next, in 42, we'll find the values of x for which g of x is equal to -1. There is a line that gives us all the points that have the same y value, -1, and that does not intersect with the graph at all, so we can either say none or we can say no solution. No solution is sometimes what we say when we're trying to solve an equation, and our equation here that we're trying to solve is g of x equals -1. In other words, find the value of x that makes that a true statement, value or values. And that's it.